Okay, for people joining the live stream, we are reviewing numerical computation functionality for the upcoming version of Wolfram Language. So, is this mainly about optimization, Roger?
Well, I'll answer for Roger. Yes, it's mainly about optimization, but I think we should actually do the differential equations.
No, I don't think we should, Rob. Because I think it will divert us. So yes, it's mainly about optimization, and that was where we should focus the bulk of our work today, or all of our work. And then there's a small thing at the end. That's another topic, which is something required for differential equations. Okay. So can I just, I'll just talk through a little bit here in the beginning to get us going.
Okay. Yep.
So this is, what we've added is several classes of convex optimization problems. These are a little bit specialist functions, but they are in fact integrated into find minimum and minimize in those 12 functions.
That means it's new that that's happened.
That's new that that's happened. So to give a little bit of background, the old classification of optimization problems usually talks about linear and nonlinear optimization.
Mm-hmm.
Starting in around late 80s or the 90s, it sort of became clear that there were new vistas of very efficient classes of optimization problems that can be solved fast, both in theory and in practice. And you might recall things like Komarker's algorithm,
right,
in the mid 80s that did for linear programming. That got generalized to convex optimization.
Mm-hmm.
So you can in fact get polynomial time algorithms for convex optimization problem, and it's sort of well understood when you can get that or what is required to get to that. So the new classification is convex and non-convex optimization, meaning
so that means the polyhedron, the polytope that defines the conditions is convex. Is that what that means?
Yes. So if the constraint, if you have only linear constraint, that defines a polyhedron. It might be an unbounded polyhedron, but it's still convex, and it doesn't matter for optimization whether it's bounded or unbounded.
Yep.
And but these are many more classes of things that if you're able to formulate your problem as a convex optimization problem, you can credibly say that it's solved. If you just formulate it as an optimization problem, you cannot usually.
Mm-hmm.
You know what I'm saying?
Question.
So
sorry, for the polyhedron and polygons we just looked at, do we deal with points at infinity?
Sorry? No, we don't.
Okay. Are we planning to?
We are planning to. So we're going to have more unbounded regions. Okay. So the generalized case for a polyhedron, Stephen, is that if you take the convex polyhedron, a convex polyhedron is actually the Minkowski sum, or the sum of a convex hole, which is the bounded part, and what's called a conic hole. These are raised to infinity.
Yep.
And so, yes, we're going to come to that. We have a little bit now we have unbounded regions already in the region framework, but more generally for meshes and polyhedra and so on.
Okay.
And why don't we start a little bit, and we'll fill in as we kind of go.
What are we going to? The guide page for convex optimization?
Yes, it's a good place to start. Now, these functions, what they provide are two ways to give the problems, and the output they provide, which is, there's several things to cover here, Stephen, so be a little bit patient.
No basic examples, by the way.
No, it has. It's closed.
Oh.
Okay, but the examples need another round. Okay, they're not. You shouldn't treat them as final. And these are certainly not the way they will look.
Mm-hmm.
The application examples, I think, are rather good at this point, but basic scope and properties need another round. I think the applications are really quite impressive. It will give you more than you would get in a typical class on linear optimization, and similar for all the other classes.
What do we have? We have that function for find. What is that? That's a packing function, right? What is it called? The one that, what is that function called? You know what I'm talking about? Where you're trying to find a thing given a cost. It's effectively a packing, a knapsack function, right?
Well, we have a bin packing function, right? Or
yes,
knapsack problem or something. Mm-hmm. So those are very specialized optimization problems. Now that one is a particular class of what's called combinatorial optimization.
Sure, but what I'm trying to understand is what's the correspondence in the syntax between all these various things?
Well, this follows optimization conventions. So I haven't looked at those. Specialized function can have all kinds of specialized syntax.
No, I understand that. I understand that.
But so these are general purpose functions, but not as general purpose as find minimum and then minimize, obviously. But the one thing that they do provide, what these functions can provide is also information on the dual. So for each optimization problem, there's something called the Lagrangian dual. And this provides a different way of solving a problem, but it also provides something called sensitivity. So for instance, let's say you minimize some big problem. It has, 1,000 constraints. What happens if I relax one of the constraints, give it more resources? How much better would the optimum be?
Yep.
That's something people are super interested in for obvious reasons.
Mm-hmm.
And for the class of convex optimization, we can actually do that. And it's very valuable information. So we don't have another function that's called dual linear optimization, but the dual problem is provided in all these problems. The dual information, that's what those things down below there is.
Well, so is there a minimal version of what I can call to get to run linear optimization?
Yes. So unfortunately, these early problems use the coefficient syntax. But we also support the variables. See what I'm saying? You can actually give symbolic constraints, and that's easier. And we haven't updated these basic examples, which is unfortunate because.
Okay, all right, so fine. So, but if I were to give this, so I'm just copying.
Let's say x plus y. Okay, you can just do symbolically so you can understand what the heck you do.
Okay, all right.
X plus y. Mm-hmm. And then say x minus y greater than 1. Greater than 1, and then x plus y less than 2 or something like that, 10, and then comma x, comma y. Well, that's good. It will actually return plus infinity or minus infinity as appropriate.
But why is it saying that this problem is unbounded? Which means
it means that the minimum will be the minimum actually is minus infinity. Okay,
well, this problem is definitely solvable.
Yes. And that gives you that point.
Okay, so are there other things I can ask for from this optimization?
Yes. So if you go to that list, to scroll up, stop there. So primal minimizer, it's what it returns normally, right? So.
Okay, I didn't know that. Okay, so like the duality gap, which I've never heard of. By the way, it's not auto-completing here. Okay.
So when that duality gap, and that's called strong duality. It means that the dual problem has actually the same optimal solution as the primal problem. So there's no gap.
Okay.
And that means that, one way to solve it is to solve the dual problem. And from the two of them, you get a bunch of,
Okay. Okay. Cool. All right. So, and this is now an industrial strength object. Is that right?
Yes. But there's another caveat here. So what we've been doing, we are currently using, we haven't been writing any new solvers. Okay. So what we've been doing is to make use of solvers that people have developed over quite a long time, good solvers that are available. What we plan to do for 12.1 is also to provide standard APIs so that you can use if you buy commercial solvers from places like Mosec, Gurobi, Cplex, and these places. They will plug in and you can still use our modeling framework from find minimum and minimize and linear optimization.
Is there a reasonable API? Do these guys have reasonable APIs?
We think so. We've looked at 1, 2. We think that they all have it because that's their business.
And so what is it doing? It's running. There's a process running. I mean, is it being started by start process, or how does it work?
But we don't run it right now. We plan to do.
No, I understand. I mean, is the idea that it is a WSTP connection, or is the idea that it's a start process run on the command line type thing?
We haven't gone there. It probably needs to be a library integration. It needs to be fast. They're going to transfer a lot of data. Certainly WSTP probably won't cut it.
Okay. So it's okay. So this partnerships probably needs to be involved then.
Exactly. That's a partnership. Okay. The whole thing is a partnership thing. We turn these companies into partners instead of competitors.
Right. Okay.
And we might write solvers in the future, but I think what we've added, so what's here is a massive amounts of stuff that deals with transforming problems into these standard classes and between classes. And so there's a lot of libraries here that underpins it, but we have the framework that makes it work much more broadly than how they narrowly define here is the transformation framework.
So we've had a function called linear programming forever. How does that relate to these things? Okay,
so we are going to, but not now. I think that the correct thing is to obsolete that and do a linear programming. So first of all, this notion of call it programming is a notion from the 1950s or 40s. Okay, now the whole community is changing away from programming. They renamed their societies to become societies of optimization instead of programming. Courses, everything is moving away from the tail programming because it means something different.
Well, they lost that word.
They lost that word. Okay, so we are with the new wave. Is the idea?
Okay, but so I understand the CAB here. Mm-hmm. How does that relate to the CMB here?
Well, you can just follow the text and you can see it.
It's M is A and B is minus B.
Lovely. Okay. And these other things here are somehow also supported, is that right?
Right. There's one thing we need to do before we can obsolete it, and that is to do
integer linear programming.
Right, exactly. Okay, and the idea is that we will generally do integer and mixed real and integer for all of these problem classes.
And so in the constraints, you'll say elements of integers and things, or what? How would you specify it?
Yes.
Okay. Well, fair enough. Okay.
But that's another step. You see, to actually these convex optimization problems, they have an amazing property. Let's say you solve it over the reals, and you just round it. You can actually get the bound from the dual that tells you how bad off your approximation is. So you know how far away you are from optimum in the worst case.
Right. That's
an amazing property of these guys. And so,
okay.
Nevertheless, to solve it correctly, with integer and mixed integer, there's real work that needs to be done.
So I don't quite understand. I mean, when you give these things with constraints and so on, I mean, other than just knowing, oh, that's a quadratic programming problem, or that's a conic programming problem, how? I mean, what use is it to the user to have all these different functions?
Can I answer that one, Roger? Yeah. I mean, I think that's a really good question, Stephen. And the real use in these functions, I mean, if somebody just wants to get the minimum, they should use n minimize or find minimum. Okay, done, problem solved, easy. If they want information based on the dual and more details of the problem, they should use these solvers. And these solvers provide slightly different, ways of presenting the dual solution that is useful in particular types of situations.
Okay.
Also, if you're writing a program that's going to call a problem class programmatically, that probably means it's sort of a high performance kind of situation. You want to be guaranteed that it hits the right problem class with guaranteed performance. that's much easier to manage these lower level functions than the higher level one.
All right. So I mean, things like asking for the exponential cone is irrelevant for linear optimization. Is your point? I don't even know what.
Yes, it can't be used. It can only be used in conic optimization. The only one that can handle that particular type of input.
Okay. Okay. Well, yeah. All right. Let's look at these constructs here. I mean, unless there's. I mean,
by the way, so there's one. No. I mean, it's lower level. But one thing, if you just want to look at something, if you look under application, there is a subsection under each application that says problem transformations or standard problem transformations. Okay, basic modeling transformations. Okay, we have one of those for each, and that tells you how you map a variety of problems into this problem class. Okay, I think it's more for expert use, but that's the kind of thing you would learn if you're serious about optimization.
So okay, so let me take this example.
You picked the hardest case, Stephen. Conic optimization is the most sophisticated of it.
Okay, so you're optimizing. What does this mean?
Okay, so this is what it uses there is called an epigraph transformation.
Okay. What's even the statement of the problem?
Well, it was there in text. It was there in the text for the example that you looked at.
Okay, that's the objective function t.
Yes. So now you're going to minimize t, okay? But we really wanted to minimize the absolute value of x plus y, okay? So you see how this transformed it? You added a new variable t, and that t minus t and t bounds x plus y.
Okay.
Okay, but that's the same as saying that you're going to minimize, absolute value of x plus y.
Okay, so if I were to say find minimum, or should I be using n minimize?
Either should work fine.
What happens if I use minimize?
Well, it will work too, but it will use not efficient. This is only numerical algorithms.
Okay, all right, n minimize. Okay, so you're saying I'm really trying to get abs of what?
X plus y.
Minimize that, subject to the constraint.
Okay, but you have to have another level of brace around the two pairs.
Sorry, this is that thing with a constraint that xy is an element of a disk. Is that right?
And that can actually just be the variable declaration for n minimize as well. You need to use the disk they provided that doesn't include the 0 point.
Okay. Okay, so did this use the same code path as this?
Essentially, yes.
So if I were to go, for example, how do I get an n-dimensional bool? Oh, I just put a bunch of things in there.
Right.
Okay, so if I say table 1, 6. Oh God, how do I do this?
Well, you could
just use x as a single vector variable. And I don't know if this is going to work because I don't know if we have ball hooked up and then you do total of abs of x.
No, abs of.
Total of abs of x.
Right, total of abs of x, yeah, sorry.
That would seem to be a little baguette there. So with one of the, what's that?
Yes.
Should I send you this?
Yes, do send me that.
Okay, do you think it got the right answer? Who knows? Well, anyway, it doesn't matter. But okay, but so this in principle works, and it's feeding itself into potentially I mean, I'm just trying to understand these code paths. This thing is feeding itself into this same. So, to what extent, from nminimize, can I reach all of the default property features of these various special solvers?
No.
Okay.
No, you can't get the dual and things like that because it's
no. I said the default property. That is not the special, not the stuff that requires.
I see. Okay. Yes. Yeah. So here's the thing: if it's recognized, okay, in minimize or find a minimum, then it will use those same code paths.
Right.
Basically, I'll tell you how I did the code path for this, Stephen. So what nminimize does is so I've sort of set up a structure that holds what I call an optimization problem. Okay, and that's how all these solvers are handled. So what nminimize does is it constructs one of these constructs. It tries to do the transformations, which gets it into one of these solver forms.
Okay. If
it succeeds in doing this transformation, it calls the solver. Okay, and if the solver succeeds, end of story. It's done.
Yep.
Otherwise, it goes back to the other method, the default methods nminimize always used to have. Or if somebody specifically specifies some method, then it'll use that method, obviously.
Right. Okay. Sounds great. All right. Let's go on and look at these. Unless there's more stuff we should look at here. I mean, I think I can be very helpful with all those dual, unless they're naming issues with all those dual whatever things.
I don't think so.
I know nothing about that stuff. I never heard of primal values before. Sounds.
Well, it's sort of an optimization-y type thing. They talk about the primal problem and the dual problem.
What does dual problem mean?
It is a related, so it comes from Lagrange multipliers, if you remember those.
Yes.
Okay.
In the solver pages, we have a little explanation of what the dual problem is. It's general for all of these.
Yeah.
Okay. All right. Okay. By the way, okay. So, various people are asking various questions on the live stream. Let's address those before we go on here. One is asking for, can we add one of the following optimization methods? Tree Parsan estimator. I've never heard of this. Gaussian process surrogate or random forest regression.
Okay, we should send them in. That's not the project we're doing now. Optimization is a wild and diverse field, and so none of those have any reliable performance characteristics. That doesn't mean that they don't
type problems.
Right. Yes. It doesn't mean that they don't work. They have problem classes for which they work great.
Well, random forests we are using extensively in machine learning.
Yes.
I mean, that's supported by classifier and things like that. But is that...
Absolutely. That's not here.
No, I understand. But is there any interplay between what by the way, we got a bunch of weird background noise that maybe Rob...
Yeah, so a lot of these things, the standard application example we have for each of them is to solve classification problems and fitting problems and so on. Those are standard kind of fair problems.
Right. But so I guess I'm asking the question, okay, so those are problems like fitting, let's see, so things like fitting, which eventually become things like quadratic optimization problems and so on, if I'm not mistaken, are we also sort of using these new solvers for those or not?
Okay, so two answers there. One is that we actually have here updates to find fit and fit that uses that extends them to support what's called regularization. Let's talk about that a little later, as we work our way down the page. So we have updates there, and then we have a much larger set of updates planned for 12.1 in terms of seeding all the in-house teams with solutions using this new technology.
Okay.
So that applies to almost all teams, and we'll see that start to kick out in function all across our system.
Okay. All right. Vector greater or equal.
Okay, so these vector inequalities. So there's two things. The reason we introduced them here is that they provide a modeling framework. They provide ways to write optimization constraints using vector variables. And
what the hell is that? What the hell is that? What just happened there?
Well, this is an old page, unfortunately. I mean, it's not an old page, but that is probably not the correct. Not
glyph.
Yes. Well, I'd say you've got an old build.
Is that
really
what's going on?
It's from yesterday. Well, let's say vector greater or equal. Let's just say vector greater or equal xy. Okay, it doesn't have a print.
So now you actually need to have a list brace around those two. Stephen, you need to actually put them in a list.
Those?
Yeah.
Why?
Okay, I'll come to that in a sec.
Okay.
Okay. So the core motivation is this allows you to formulate a lot of these problems cleanly, and you get sort of a high level and fairly efficient language to formulate them. The other thing is that these vector inequalities are quite fundamental in that this is the class of, they're partial orders, they're not total orders. That's why they're not sort of overloading, less equal and so on. So they can return false, either because they're uncomparable or
okay, so there's some other condition here that subscript kappa.
Yes. Okay. So the point is that this is the class of all possible vector inequalities that are also compatible with a vector space structure. That means that if you have an inequality x greater than equal to y, and then you can add a vector z on both sides, and it's still true.
Yes.
And you can multiply the left and right hand side with positive numbers, and it's still true. If you enforce that, and that almost everything in scientific computing, technical computing, relies on a vector space.
Mm-hmm.
If you enforce that, they're necessarily defined by a convex cone, a proper convex cone.
Okay.
So now you can have other kinds of inequalities. The default case is just like x is greater than or equal to y if x1 is greater than y1 and x2 is greater than y2. But for instance, for matrices, you can have the space of positive semi-definite matrices. And one matrix is then greater than another if their difference is a positive semi-definite matrix. Okay.
Yeah, okay.
And that space of positive semi-definite matrices, that is a cone. That is a proper convex cone. So it defines a proper, inequality.
Something is broken.
Something has horribly gone wrong with the typesetting.
Well, the parsing as well.
Yeah, the parsing of the typesetting.
What's the precedence of that operator?
That's a good question. I think if Itai was here, he could immediately answer that.
What should it be? And by the way, was it put in the syntax table?
If it hasn't been, it will be shortly. And likewise, the character pages will be put in shortly.
Okay, but I meant the syntax table that has been,
I understand.
Put prominently, but that used to be in the appendix of the book.
Right. So. It's a good reminder. We need to get it there, obviously.
Okay, but the question: what should its precedence be relative?
I think it should be relatively close to our other inequalities.
Should it be I think the other inequalities. Yeah, the other inequalities have this strange property, right? That if you say x greater than or equal to y greater than z,
Yes.
right, that thing turns into that.
So I want to return to inequality, but not now, but very soon, so we can sort that out once and forever, because that's it's sort of needed, but it's undocumented.
Right. So we have a similar construct for these vector inequalities, and it's set up as developer vector inequality, but we have rules so that basically always evaluates to either inequality, which once we deal with that, that'll be great, or the individual vector greater or equal, et cetera, et cetera.
But so how do those, I don't quite understand, because you have to have a 3 argument. If you say A greater than B greater than C, right? So that means that in that list there are several things, right?
Yes, you can have several things there. You can have any number of things to compare with the same operator there.
Right. So by the way, the fact that you're giving this, I mean, by the way, you really should give in the usage message. You should give the typed out form of these as well.
But less, we probably should. But less, greater equal doesn't. Okay, you never see that form is not available anywhere.
Okay, well, perhaps it should be, but at this one, it's much more obscure because somebody's going to look at this. They're not going to see the little squiggly,
No, I agree.
Flare.
Right. I think you're right.
Right. Well, that's what the table 2 down is supposed to do.
Yes.
Sandra on her live stream helpfully points out that you can just do that. Ooh, that does not look right to me. That does not look right at all.
Yeah.
By the way, Sandra on our live stream also points out that this answer is correct, even despite the complaining.
Okay, thank you, Sandra.
It's still a bug, but it's
okay, so this is wrong.
Yeah, I think we need to look at that. But you look at there was a lot of things wrong there in this build.
No, I understand that. So I'm asking this question. When you type this in, does it really support subscripting the operator? Because I don't think we support that for anything else.
Yes, Itai set it up so that it indeed supports subscripting. You can subscript or underscript the operator, and they're both supported.
That's incredibly exotic. Okay.
Well, we support that in a bunch of operators. Sum supports it, product supports it, integrate supports it, partial D.
Wait a minute, subscripting?
Yeah. How else do you type these things in typeset form?
Oh, you mean I see, but it's exotic for an infix operator. What other infix operator does that?
Well, I don't know if we have any other.
Listen, I would like to sound a concern about it because I don't know how that's supposed to work, and I have a bad feeling something might go wrong with it.
No, but that's part of why we have the extra level of list there, because then it's structurally parsable. I mean, a lot of concerns with parsing were addressed. Do you see what I'm saying?
Yeah. Hey, by the way, on that live stream, someone is had asked before about better ways of distributing numerical optimization across large AWS compute instances, for example.
That's again not something we've looked at. No, I don't. I agree with that. That's a valuable thing to do, but it's a different kind of project.
Fair enough. I mean, obviously, if you just get a very big, crunchy computer, server computer, you can run this. I don't even know how do these parallelize across? Do these parallelize well in parallel environments? I've not heard of that. I mean, in other words, when I hear about like the giant, airline optimization stuff of old, I thought that was just done on one very big computer. I didn't think it was done in parallel. Do these algorithms parallelize? I don't know.
It's another project to look into.
I think if it's reasonably doable to make them parallelizable, then the commercial solvers will have done that, and when we hook up to these commercial solvers, we should be able to make that available.
A lot of these things that parallelize, they do it because they don't really work that well. So you need to kind of start from multiple points, or you need to, there's other ways to break the problem too, that you update this part here, you update this other part here, you come together, then you have an updated state, and you move from there.
Yeah. Okay. Well, anyway, all right. So that's for the future. Okay. Again, I strongly believe for this particular operator, it's very important to say up above here, vector greater or equal, or this funky form. Okay. Makes sense? Yes?
Yes.
Rob? Okay, so I have no clue what any of this stuff means.
Okay. So this was a pivot we did last week. We first had these cones as actual objects in the system. We decided that they didn't warrant that, so they're now just these forms. And if you look at the first one, that's the non-negative cone, that's the standard vector greater equal. Because look at the second input form up there at the top in the brown box. The fact that x is greater than or equal to y is the same as that the difference is in that cone.
Okay, I understand.
Okay. That's exactly how the cone, and conversely, if you had one of these inequalities defined, they actually define a cone.
By the way, why do you need that n there? Presumably you can just see what the dimension of what the length of those vectors is. And presumably you can just say non-negative cone.
Yes, you can.
So you should document that. Oh, you do. Okay. But so for norm cone, can you also do that? Yes, surely you can. Because it knows which Rn you're talking about by just the length of the vectors.
Right. If you've specified the length of the vector elsewhere, if it's a symbolic vector, and you don't have the components of it, it's not a list. Okay.
I see.
It's an X. If you've specified a length elsewhere, or other parts of the problem uniquely define that length, sure.
Non-numeric is hyphenated. There's a trivial fact for you. Okay. Okay. All right. What else should I pay attention to in these functions?
I think that's it. They will come into play. There's a large number of other areas that are much broader in the system. We've currently integrated them. They also work for the symbolic optimization function. They work for reduce, solve, all of these things can now take these specs. It means that you can also integrate using bool and other things, kind of works with these. They are, in fact, very useful to specify multivariate conditions of various kinds. I won't go into that now, but it's a whole slew of things that
you should check that knapsack function to make sure that it's not insanely inconsistent with what we've got here.
I will. But as I said, I don't really care about these special solvers because they don't solve general problems.
Yeah, I understand. But we should just make sure that from the point of view of the design, that it's not incompatible.
Sure.
Let's just find out what that function actually is. Just a second. I should remember it. We took a long time naming it.
Knapsack solve.
Is that what it was finally called? That was the most obvious name. Okay.
Yeah, see, this one specifies, in a way, yeah, it's very specialized how this is formulated.
Fair enough. So I wonder if there's anything to learn from this use of an association here. I mean, like when you have categorical variables.
I think if you're not giving sort of a general optimization problem, or if you're doing something more special that's focused on one particular application domain like this, sure. Mm-hmm. Because you're going to give basically a bunch of data of various kinds, and that's a
All right,
useful
let me
way to
ask
get-
an outrageous question. How are we doing with units support for these things?
Well, I think optimization functions generally support units, right?
Really?
Find a minimum, doesn't it support units?
I don't know. You tell me. I don't know. So are you telling me if I say this and I say quantity here?
No, but that's not an optimization function. That's
Well, I understand. Okay. But I think greater than supports units, right?
I bet it does.
That's cool. Okay. Do you think vector greater or equal does this too?
No, I don't think so.
Okay. So
It could easily do.
Yeah.
Well, it should.
But I don't think it does, right?
Okay, fine.
I don't. Well, I think that's just a restriction I put on the code. That so one of the things these things don't do is they don't evaluate, and this is really important, is they don't evaluate if any of the inputs are symbolic. So probably my restriction of symbolic catches quantity, which it should not do.
Right. Okay, fine. Okay. So minor issue.
Mm-hmm.
Okay. Okay. Wonderful. All right. Should we look at the I mean, that's great. Okay. So bool.
I'm just saying that, so for integrate bool, you can give, if you want to integrate sort of over the first orthant or something like that.
So if I say vector greater xy, comma, well, let me just understand something. So if I say vector greater x, comma, 1, 1, for example, and then I say, well, if I were to just say region plot of that x element.
No, okay, so there's a different restriction. I just found out too, okay, that region plot and region plot 3D doesn't support region argument in the second case. So I'm saying that x elemental disk is not supported.
Okay.
We will add that, but that's a different missing feature, if you see what I'm saying. So, but if you do explicit x, comma y in a list,
yeah, then I'm sure it will work.
In iterator.
Yeah, so then if
so
I say,
it's a different story, but
yeah, okay, fine. That's slightly useful for understanding what these vector thingies are. How do I see something be a cone or something, or be another? So vector greater, if I say dual exponential cone, not having any idea what it is.
Right, so that's a 3D thing, first of all.
Oh, okay, well, can I try a norm cone?
Yeah.
Fascinating. Well, it seems like a useful example for the documentation if you don't already have
right.
one.
If you use vector less equal, if you look at the application example, it's a little bit more filled in, but there's over the next week or two, there's several more things coming in. But if you go vector less equal, look at the applications, you'll see a variety of things like that.
Okay. Why I mean, that little squiggly, sort of broken nose there thing, whatever it is that just a numerical error?
Yes.
Okay. And how would I get it to not have that? Is that a problem with region plot, or is that a problem with vector greater?
It's a problem with region plot.
Okay.
And so you need to have...
okay, just more points than region plot, that's fine.
Right.
Okay. Okay, that's cool. So if I were to say region plot 3D, I could see one of these fancy dual exponential cones.
Yes, actually go to vector less equal and you have a whole gallery of them.
Okay.
Okay, so now if you go to either properties or applications, there's starting to be more. This is because of a pivot. So if you look here, there you see the gallery of cones, basically.
Okay, cool.
And this is you can see it's not quite updated because these are the objects that we've decided not to introduce. There's going to be strings instead.
I see. That's a power cone with a certain exponent for its norm there,
Right.
or something.
Right. Yes.
Okay. Very nice. All right, let's go back to the agenda.
Now, there are, okay, this is talking about the future. We've talked a little bit about it already.
What's the machine learning play with these things?
Well, so there's going to be increasing things, but one thing right now, Rob, why don't you talk about that?
Sure, I've contacted ATN, and I've looked at some of the basic, like the linear layer stuff they have, and trying to figure out what they've done. Basically, with the new stuff I've put into fitting, we have from faster to orders of magnitude faster than what they're currently using for that. And I'm hoping to talk to them when I'm in Champaign next week, to see what other possibilities there are. But that's just one clear example
of where right now it's using some kind of steepest descent backpropagation thing to solve.
Yeah. And there's so in the new fit, there's a really interesting method for doing these basis pursuit type problems that I put together. And it's based on sort of sequential, doing quadratic optimization multiple times, and it's really fast.
Okay.
And it can handle huge basis problems. And the code they have now, it would just completely bog down with that sort of thing.
Okay, well, that's great. All right, let's just very quick look at whatever you were doing in nonlinear PDEs here.
So the big news, the big actual feature is that we now support solving nonlinear PDEs over arbitrary regions. So this is basically finite element, but for nonlinear PDEs.
That's impressive. Okay.
Okay. And one thing that we need there is the one symbol that we need to introduce is a starting guess. And it turns out that there is it came up in this project when you have nonlinear PDEs and you specify boundary problems. It's not necessarily a unique solution. There are multiple possible solutions.
Don't we have this in like a million places, like even in find minimum or something? We've got an x sub 0 that we're specifying in the variable in the in the specification of the variable.
You're right. Okay. So the question is, should you start making that part of the problem specification? And if we without going out to optimization right away, so just think of differential equations. Boundary value problems in general have this feature that there are more than one solution.
Whatever happened to our vaunted PDE special function effort? The Helmholtz equation, getting me an actual, just a function called Helmholtz equation.
We can return to that, Stephen, but the boundary conditions is going to be massive.
Okay, but still, I have to remember how to type in this.
I know. So we're gonna, what part of what we want to do is to have more special operators, and we could still do the special functions case, but special operaters means that
I'd be happy with special operators. The heat kernel or whatever.
Right, and and that's our goal. Okay. To do that modeling project, it's going to make it easier for everybody to do the modeling side of these PDEs.
Yep.
But going back to starting guess, okay. So boundary value problems is a typical thing that you have multiple solutions and the question, which one are you picking out? There's another case, which is when you have these over-constrained systems, if you like. It's almost impossible to find a consistent initial condition. In fact, that's a massive part of what the system modeler product solves, to find initial condition. Because these DIEs, you're on some manifold that's much lower dimensional than the number of variables that you have. What's your chance of hitting that?
Right.
Probability 0, right? So you need some help. And so that's in fact built into the Modelica standard even, that things are interpreted as initial guesses. And we have had kind of hacky method things to do this before, but I think that the proper way is to indicate it as part of the problem statement of where you start.
Yeah, another point is that unlike, so find minimum has this specialized thing for giving the starting guess with the variable. That's sort of an awkward syntax, and if you look at the documentation, it's sort of hard to figure out. Whereas in ND solve, what we typically do, and this is your design, I think was a good idea, is the specification for sort of the dependent variables is done automatically. So basically, the third argument for ND solve, or is it the second argument? I can't remember which, is actually what you want to have as output, or like ND solve value. Okay, so we don't actually necessarily even always specify what the dependent variables are.
Yeah, I
ND
understand.
solve value.
Hey, by the way, on our live stream, Ethan Black 86 points out that MXNet already uses fast solvers. So, and also makes it that the general purpose GEM system is still end of the 2.93.
I see.
Okay, so it may not be this. It may be that once the linear layer is inside MXNet, it's going very fast.
Maybe.
Yeah,
obviously. So one thing that you can do with a specialized layered software stack like MXNet is that you have to do things like algorithmic differentiation in order to compute the gradients all the way, through the layers. And that's, but they've also pushed optimization technology. They push first order methods a lot because you can't compute second derivatives. That's usually too hard with 5 million parameters. It's hard.
All right, anyway, let's go back to starting guess.
Okay.
So we really don't want to introduce something like this at this stage in the development cycle. This is a big, complicated thing that will have effects on lots of functions. Lots of functions, find instance, just tons and tons of things. I also am very unclear that this is the right semantics for it, as opposed to an option. I understand there are scoping issues with an option. We really should not introduce this right now. What is it needed for right now?
It's needed for nonlinear PDEs.
Look, okay, then we should schedule another meeting to talk about this, because this is not a 2-minute question. This is...
Sure, we'll do that.
I think...
no, we'll do that. That's fine.
It's a very weird piece of semantics.
It is slightly weird, but...
let's think about how it relates to, for example, when event, which is another weird piece of semantics in an equation setting. It's not directly related, but what this is it's telling you this is a thing that only matters transiently in looking at the equation. So in other words, it's as if it's sort of like a when event, which is just like a delta function at t equals 0, if I'm not mistaken. In other words, or isn't it even? It isn't even that. It's not even. This isn't even a value. This is not something that actually occurs for the variables in the equation. This is merely an advisory thing for, you're trying to solve this boundary value problem. The value of phi might be such and such. Is that correct?
That's correct. So it's an advisory for an algorithm that the solver may eventually use.
So most of those things we would do in options.
Yes.
Okay, so what's the reason to not have this be an option?
Well, if you want to, so one argument is, yes, you could have this down, down as a type of method option. Okay.
Well, no, forget method. It's just a regular option where it says, starting guesses, arrow, and then, var arrow expa, or var equals expa.
Could be that. Okay,
so the reason that I already said is that there is a scoping question with that. But I don't know how seriously we're scoping these equation solving. How are we scoping what are we doing with the scoping of something like linear optimization? Understand the question?
Okay, so none of the convex solvers need initial values. There's no starting guesses. That's in fact a phase of the optimization problem, to find an initial point and
they don't need them, Roger, but they can be given.
No, that wasn't the point I was making. The point I was making was a purely structural point. We've got variables here, X, Y, T. So right now there's no scope.
Okay, so Stephen, it is scoped mathematically speaking. It's not scoped if you think of programmatic scoping.
Okay, fine.
You see what I'm saying? So it's not a hold-all thing. We have many things that are mathematically scoped, but not programmatically scoped.
No, I understand. So I think what this should be, I don't see any reason you don't,
We can go down that route.
I think that's the right way to do it. Go, apart from scoping, this seems like the right level of stuff. But I don't know whether you want to call it guess. What are we calling it in the case of find minimum, for example? What do we refer to it in the documentation as?
Starting values. But see, that's really problematic in a DE setting because starting values.
Yeah, I understand. Have a meaning because there's an independent variable that might be a starting thing. Okay. I don't know what this background noise is, but anyway, I just initial guess just seems like an awfully informal thing to say. What would be a fancier name for this?
Well, the reason we came up with initial guesses, we tried all sorts of different names, is because there's something guess in the Modelica language.
Who cares?
And it is sort of we wanted to avoid starting value or initial value because
no, it's a bad idea.
It's a bad idea, right?
Well, look, I think, and by the way, Sushma, can you please report this bug that I've mentioned many times, that the cursor is not turning into a vertical eye bar?
Okay.
I mean, it would be something more like that, right? It's like assumptions.
Well, but that implies you're really assuming something about the variable.
I know, which isn't correct.
I mean, I think the guesses is not as, because really it has nothing except in the sense of algorithm. It actually has nothing mathematically to do with the solution.
Well, okay, so we could do, I mean, actually it doesn't need to be plural, right? What is it? It's a solution guess.
It's really initial value guess.
Initial value, or is it a solution guess?
Well, it depends.
It depends, yes.
So for differential algebra equations, it's a guess on the initial values. For stationary PDEs, it's a guess on the solution.
But does it typically look like f of 0 is whatever? Is that what it's typically like?
Yes. Or f of x is whatever.
Okay. And why is it? So it's an initial guess because it may be ignored.
That's right. It may be ignored.
Is it a guess for the solution, or is it a guess for something else?
It's a guess for either the solution or a point along the solution. Now, say if we were to use it in optimization as a guidance for where the algorithm might start, it would be a guess for a part of the solution or a component of the solution.
Well, I think it's a really weird option, initial guess, but it's really weird. I mean, but setting it up as an option is the right thing to do. The only question is what the right name is. And I think you were trying to avoid the word initial because it sounds like it's an initial value problem.
Yes, well, we could have starting guess as well.
Sure.
But it's, it goes back to the question of what we want to, we want something in there to indicate that it's just, to start that. I mean, in optimization, libraries and stuff, they typically call this thing a warm start.
Okay. What about initial hint?
We actually thought of that. Oliver objected strenuously to hint, but
why?
I can't remember the exact reasons he had.
Okay.
But I think that is sort of what it is.
Let's find out what objections he had to that.
Okay, let me dig through my mails.
But I mean, some initial guess, initial hint.
Solution hint.
Yeah, but that's why I was asking. Is it always solution? It might not be.
Right.
Something like this is going to work. You can set it up with a name there. Why don't we use initial try, guess, I don't know. Conjecture.
Okay, well, here are Oliver's objections. Okay, I'll just read them to you.
Yeah.
So he says, hint is not a terminology used in numerics. Also, the starting vector is an integral part of the algorithm. Hint is not an integral part of the solution. I disagree with him on that bit. Point is, a hint is something one can give, but we are looking for something that must be specified. He's not really correct on that. I mean, his point is the algorithm requires this to start, which is correct, but the user doesn't have to give that. And then his other objections are that, other PDE solvers use things like start vector, initial value.
I don't care.
Yeah, which...
I'm beginning to admit that starting guess as an option may be our least horrible alternative.
You've been going down the same path that we went down, more or less.
Mm-hmm.
Yeah.
I'm fine with starting guess. I mean, there's the initial versus starting. There's no...
Yeah, I think starting is mildly better. All right, let's go for starting guess, but I wouldn't mind picking this up again. Various people on the live stream are suggesting things like guide values, hint values, try first. Yeah, I mean, starting try, I don't think try really helps because it's actually something it's not a try as in, it's not like trying to find, it's not like it's going to solve the equation.
Right.
And that's another issue with guess. Because guess doesn't in fact solve the equation. I think that's my visceral objection to it, is that it doesn't. Guess suggests that you've got some random Diophantine equation and you can guess the solution. That's not what's going on here. This is something that's being fed into numerical algorithm that is the beginning, the starting point.
Right. Well, one other possibility might be something like starting iterate or something like that. Because these are typically always used in some kind of iterative algorithm that corrects and improves.
Yeah, well, that seems better. Look, guess isn't right for the reason I just said. Yeah, what is that background noise? It's driving me crazy. I'm sorry. I'm just.
I was sorry. I was writing myself a note. I guess my desk is noisy.
I don't think it doesn't sound like that.
Oh, must be something different.
Yeah,
I think starting iterate wouldn't be horrible.
What are you suggesting? Starting iterator?
Starting iterate.
No. Nobody will know what the heck that means. To be thought about a little bit more. Okay. Get something in we need to talk about in the next day or so. Okay, put in starting guess for now, but we're going to change it.
We'll put it in as an option for now.
Definitely as an option.
Yes. Okay. Okay.
All right.
I think that's everything, Stephen.
Okay, great. All right.
Oh, wait a minute.
Live stream. Oh,
should we?
Yes.
Rob, should we cover fine fit and?
What is there to cover there? I'm really late for something else.
Right. We don't need to. We can, if we have one more, we can.
Well, there's not so much. It's fit that changes the most.
Fit new. Fit new.
Lowercase new?
Yeah. No. Capital. Camel.
Hey, actually, this is a good suggestion from the live stream. Initial seed values. I like the concept of a seed.
That's not too bad.
Yeah, the problem is that implies the problem I see with that is implies randomness.
No, it doesn't.
No, I don't think it does.
I mean, a guess, it's no more random than a guess.
True. Yeah, initial seed values. Or why do we even need initial then? Why not just seed values?
Yeah, that's what. But actually, it's not even values because it's relations, right? I mean, what it really is something like seed conditions. It makes one sound like it's planting a dicotyledon or something. Never mind. I like the idea of seed. Seed is better than because it's something that things are going to grow from in a somewhat undefined way. Also a suggestion on the live stream for initial nudge, but I don't think that's right because nudge suggests you're pushing in a certain direction, which this is not. I think seed is the right concept.
Starting seed?
How about, so we have random seeding, right? What about initial seeding? And then you say initial seeding is X is 6.
That's fine.
I'm reasonably happy with that. Thank you to Wild Animal Channel who suggested the seed idea.
All right, so do we want another meeting on this or should we just do that?
Do that for now. I think we should have another meeting just to finish off whatever you needed to finish off here with fit and so on. Okay.
Fine.
Okay. Thanks. Great stuff. Thank you to folks on the live stream. Thanks for those suggestions. All right. This background noise is driving me nuts. Okay. I'm going to be happy to get off this We are going to, for those on the live stream, if you're interested, we are working on chemistry next in just a moment.